where the density function increases linearly? Did we do one of those? What was the electrical field as a function of R? Or which one did we do if we did it? So in essence, you're relying on utilizing Gauss's law to first find the electrical field inside, right? Then you're integrating that to find the voltage inside. You see? So this would be non-uniform sphere. I believe this one, the electrical field comes out to be like this. KQ over R to the fourth R squared. I think this is the one that we had done. So because the density is increasing as R, the electric field ends up increasing as R squared. But then when the little r is equal to the big R, you still get it equal to KQ over R squared. So it always has to be continuous. So the electrical field looks like this. The square function, then proportional to R squared, and then here, proportional to 1 over R squared. Okay. So then, well, if I want to find the voltage inside, so I know outside what it's going to look like, the 1 over R. So what kind of it's probably going to look something like that again, you know. So then we do the same thing again. V sub big R minus V sub R is negative integral KQ over R to the fourth R squared dr from R to the R. Right, so then here you put KQ over R, negative KQ over R to the fourth, R cubed over 3, R to the R. So you take your electric field that you got from Gauss's law, put it there, integrate it. Then put the R cubed there. Plus KQ over R to the fourth, R cubed over 3. And then the R cubed cancels all but one of the R's. Then everything goes to the left side and this thing comes to the right side. And you add these two. Okay, then you get 4KQ over 3R minus KQ over 3R to the fourth R cubed. So yeah, it does look like a function that's kind of coming down, but it's coming down cubically. So where does it start? It starts 4/3 KQ over R. The other one started out as 3/2, right? So the other one started out, this is KQ over R. The other one started 1.5. So if this one was 90 volts, right? And then this one was 45 volts. So this is R equals 1. It should go like this. Draw it to nice and scale. This is 2. So I shouldn't go down that much here. Because the voltage is not a 1 over R squared. So go down less steep. would say. Then what's going to be the voltage here? Well, when you put R as 0, you're going to get 4/3 of 90 volts, right? So I'm using back the same sphere that we had before. So then that's going to be 120 volts. So that brings it even lower than before. It's like something like this. The other one was 135 volts. So 120 volts. And it kind of maintains its value for a longer time. Then it drops to it decreases like that. It's a cubic. It's kind of like an inverse of a cube. You know how a cube goes like this? Like it stays flatter longer, but then it starts going like y equals x cubed. Well, this is the inverted version of a cube like that. It stays up there for longer. The voltage drops less. Then it drops steeper until it gets to the surface. Then you get the 1/r behavior. So we would say this is proportional to negative r cubed. Okay, and then you can solve problem like you could say, okay, 1 nanocoulomb charge is placed there. If it's displaced, what is its speed when it reaches the center? Then answer it in the same way. So once you've got this figured out, then you can answer a similar kind of question. The only question you can't answer is if you have a negative charge and if you displace it, what's the frequency of oscillation, right? What's the frequency of oscillation? Because the electrical field is proportional to the displacement squared. Ugh, that's nasty. That's a harder differential equation to solve. So forget it. Only the uniform, you can ask that.